next thing that we want to talk about is the sum rule. And the sum rule is going to come from OR type operations. We've actually already been implicitly using the sum rule when we've decided between three t-shirts, well, we're summing up all of the elements in that set. This is something we've already kind of been doing implicitly, but now just to make it explicit, suppose that I have 3 pairs of shorts, or I could wear one of 2 pairs of jeans. You know, how many ways can I put on a covering for my lower body? Well, that's going to be the size of the first set plus the size of the second set, because they're, you know, different things. So this is going to be 3 plus 2, which is 5, because I'm either in this set or in that set, but I'm not in both. So in order to compute the number of ways to do something when I'm using an OR operation, I'm going to sum, I'm going to add. So let's do a quick example using both the sum rule and the product rule, just to combine things. And that is, let's suppose a valid product code is either, so it's going to be one of 2 things. Either we're going to have 2 letters followed by a number, or we're going to have 1 letter followed by 3 numbers. And of course, I'm going to emphasize here not both. And what is a number? Here I mean 0 through 9, and letter here I mean A through Z. Okay, so how many letters are there? Remember, there are 26 total letters. That's something that students of this class tend to forget sometimes. So how do we do this? Well, I've either got to follow the first routine or the second routine. So for the first thing, I've either got letter, letter, number, so alpha, alpha, hashtag, or I've got letter, alpha, followed by 3 numbers. 1, 2, 3, hashtag, hashtag, hashtag. So I've got 26 times 26 times 10 plus 26 times 10 times 10 times 10. So I'm either choosing a letter, then choosing a letter, then choosing a number, or I'm choosing a letter, then choosing a number, a number, a number. Notice I said nothing about whether letters could repeat or not. So we're not worried about, you know, if I chose A here, can I also choose A there? Yes, I can. I haven't explicitly forbidden that. So my final answer, as I would like it, is going to be 26 squared times 10 plus 26 times 10 to the third. Okay, you can multiply all this out, and that's great, but I really want to see where your numbers come from. That's kind of the main thing that I want to see with these types of questions. The numbers are going to get so hilariously large that I'm not going to really care about precisely what they are. I want to see how you got there. Presumably, you could type this into a calculator and get some numerical answer, but I don't really care about that numerical answer for just verifying that you understand the concepts. All right, so that's the basics of the summation rule, the OR rule. So next I want to go on to inclusion exclusion, or the complementing rule. So I'm going to give you a formula, and this is called inclusion exclusion for 2 sets, and it's basically the size of A union B is equal to the size of A plus the size of B minus the size of A intersect B. And I want to give you a quick sort of justification, not quite a formal proof, but a quick sort of justification of this. So suppose I have one set A and I have another set B, and I want to know how many elements are in the union. Well, that's how many elements are in this whole MasterCard symbol, right? Well, let's shade A up and to the right. and let's shade B horizontally. All right, now if I want to count the union, let's just count how many elements are in each region. Well, I've counted the number of elements in this region, counted the number of elements in this region, and counted the number of elements in this region. Okay, summing those up gives me the union, but now how do I get the size of the union from these other sets? Well, if I sum up everything in A, I've counted this region and this region. Then if I add up everything in B, I've counted this region and this region again. So this middle region has been counted twice. So to get an accurate count, I need to pull it out. So I've counted it twice. If I pull it out once, then I've counted each region exactly once. So it's just a quick justification for the inclusion-exclusion rule. Now let's try to apply it. Okay, again, like all of these, this is complete fiction. We're going to suppose that I have only 10 apps on my phone. Okay, this is obviously totally fictitious because there's no way that I could have that few apps. Now, since we're already in fantasy land, let's just pretend that 5 are free and 7 are games. Now, I shouldn't have to say this. You should all know this, but obviously the only apps worth buying are games. Nobody doesn't know that. If you're spending money for an app and it's not a game, you're living life incorrectly. Okay, so now the question is, how many free games do I have? On my phone. Well, let's write down what we know about these sets, and we'll write down the inclusion-exclusion formula, and we should be able to pull this out. Now, I'm sure a lot of you can do this in your head, so it's not so much about how many free games do I have in this fictitious scenario. It's really more about, can you apply the inclusion-exclusion formula? So let's call the free games. Let's call the free apps F and the games G. So the size of F is going to be 5. The size of G is going to be 7. Now, I want to know the size of F intersect G. What's the other piece of information I have? This. I have that the size of F union G is going to be 10. So I have that 10 equals the size of F union G, but F union G, by inclusion-exclusion, is the size of F plus the size of G minus the size of F intersect G. Now when I plug everything in, I get here 10 equals 5 plus 7 minus this quantity that I want to know, F intersect G. Doing some really basic algebra here tells me that F intersect G is going to be of size 2. That means I have 2 free games on my phone in this fictitious world. All right, so the next question is going to be a 3-parter. So let's consider the natural numbers from 1 to 100. Sounds fine? So part A, I want to know how many are even. Part B, how many are multiples of 3. And part C, how many are multiples of 2 or 3? So for part A, well, how many are even? Well, basically what I'm going to do is I'm going to take the numbers, I write them down, 1, 2, 3, 4, etc. And I notice that every pair has one even one, and it's the last one. So I want to know how many pairs of numbers are there between 1 and 100. Well, that's going to be 100 divided by 2. And I want to make sure that I'm always getting the last one. So I'm going to do the floor of 100 divided by 2. I know this is redundant, but I'm doing the floor of 100 divided by 2 because I'm counting pairs and I want to make sure I'm getting the last one in each pair. And this is 50. So the answer to part A is going to be 50. Part B, I'm counting triples, 1, 2, 3, and I want to get the last one from each triple. 4, 5, 6. And we notice as I get towards the end, I'm going to have, let's see here, 97, 98, 99. Well, that's going to be one of my triples. But then 100 doesn't fit into a triple. And this is, again, hopefully you'll see now why we have to have this floor. To find the number of multiples of 3, I'm going to have 100 divided by 3, and I'm taking the floor because I don't want to count that guy. And that gives me 33 multiples of 3 between 1 and 100. So now the question is, how many multiples of 2 or 3 do I have? And this is sort of the point of this exercise. Well, let's suppose that even numbers are called E. So the size of E is 50. And multiples of 3 are called T. So the size of T is 33. Now let's approach part C. Part C is asking us for the size of E union T. Well, what is the size of E union T? Using inclusion and exclusion, it's the size of E plus the size of T minus the size of E intersect T. All right. Well, I could plug everything in except for E intersect T. What is E intersect T? E intersect T is multiples of 6. Because it's multiples of 2 and 3 is the set of. That looks bad, is multiples. It's the set of multiples of 2 and 3, also known as multiples of 6. Well, we've already got a method for computing multiples of a given number. We're going to take 1 to 100, divide it by 6, and then take the floor. So what is 100 divided by 6? Honestly, I don't know. I'm going to do a little bit of scratch work. Okay, I have the answer written down, but let's just do a little bit of scratch work. Let's review some longhand long division. Let's take 100 divided by 6. 6 goes into 10 once. 6 goes into 10 once. I got 10. Sorry, I've got 6. I subtract this off. Now I bring down the 0. How many times does 6 go into 40? It goes in there 6 times, and I've got some remainder. Right? I'm going to subtract this, and I've got some remainder. Which means that the answer to this is going to be 16. So this tells me the size of E intersect T is 16. So let's plug everything in. I want to find E union T. So the size of E union T is the size of E. Well, the size of E is 50, plus the size of T, that's 33, minus the size of E intersect T, so minus 16. And if I take 50 plus 33 minus 16, then that's going to be 67. And that's my final answer for part C.